In this session, we'll be looking into multiplication and division operations of unsigned numbers, and we are going to just look into two different methods of multiplication. One is slow multiplication, the other one is fast multiplication. So slow multiplication is the multiplication technique that we normally use with decimal numbers, right? So how we actually work with decimal numbers when you do multiplication. You have two numbers, one called as multiplicand and the other one is called as multiplier, right? So you can just look into this box wherein you have the multiplication done with binary numbers. We have multiplicand and multiplier, and in case of decimal numbers, how we actually proceed with this, we just take the multiplier, take the multiplier, and here you have 3 in the multiplier, that is the lowest position, that is unit place has got 3. So take this 3 and multiply with every digit in the multiplicand, and you proceed with the next digit in the multiplier, and again just leave this position, right, or shift this one position right, and then do the multiplication and add. You're going to take this 1 and multiply this multiplicand, and you get the result as 1, 4, 3 in decimal. This is how you do in decimal multiplication. The same thing is going to be done in the binary multiplication also. So this is a bit slower method of multiplying things. I'll tell you why it is a bit slower later. Right? Just for now, you try to understand how this multiplication is done with binary numbers. So you take the binary equivalent of 11, and binary equivalent of 11 is 1011, and one thing that you have to note down here is you are working with unsigned numbers. So the last bit is not going to get you the sign, instead it actually adds up to the magnitude. So this 1011 is equivalent to 11, and 13's binary equivalent is taken here, it is 1101. So now what we do is we'll just take the LSB. This 1 is considered, and you just multiply this 1 with every bit of the multiplicand. So if you have 1 here in the multiplier considered for multiplication, what we do is we just simply take the multiplicand in the partial product. Okay, I hope this is easy and understandable. So if the multiplier bit is 1, then you're going to just have this 1011, which is multiplicand here, copied to the partial product. Right? And in the next step, what you do is, before you consider the next bit in the multiplier, you just shift this one position right, meaning that you just leave this blank or just have 0. Okay, so that is what is being called as shifting. So you just shift the number and proceed with multiplying the multiplicand with the next bit of the multiplier. So what is the next bit of the multiplier here? It is 0. So if it is 0, do we need to add this number with the partial product that is already existing? No, adding 0 is not going to get us any fruitful result. But then having the 0 entered here as in the partial product is important, because you need to shift the bits here in order to have the next multiplication done and added here in the partial product. I hope this is okay, you are able to follow me. Can anyone please respond? Yes.
Yes.
Okay. Now proceed with 0. So 0 multiplied with any binary bit is going to get us 0. So you just put zeros here. And now leave for the next partial product. What you're going to do is leave 2 blanks or just add 0. Okay. So that is what we've done here in decimal product multiplication also. So just 2-bit positions are shifted. So you just shift the sum of these two things and shift again. So you get this number. So get this number added with the third bit of the first partial product. So now you take 1, multiply with all the bits here in the multiplicand and copy it here. So if this is 1, you're simply going to copy and have it as the partial product. And again proceed with the next bit here, multiply, leaving 3-bit positions, and have it in the partial product. Now sum of these values. So sum of these values will get you 143, which is this one is the binary equivalent of 143. You can check it later. Okay, so this is how basically the multiplication is done. So the very idea of adding the partial product is important here. So how you actually add the partial product? So you always just keep shifting one position right, isn't it? So you just shift this bits every bit one position right at every step, and then do adding. So here how the algorithm is implemented is, you just take the 3 registers. One is accumulator, this A is accumulator, and this is quotient register, which is called as Q, and this is multiplicand. Multiplicand will that'll get stored in one register. And you also have a carry bit, because during addition you may have a carry over here. So to store that carry, we just have another flip-flop, or it is a single bit register which is going to store only one bit, which is a carry bit here. Okay, you just look into this flow chart, then it will be more clear. Let me just zoom it so that it will be clear. Now coming to the flow chart. I think the flowchart is clearly visible to you.
Yes,
So let me explain the algorithm, how it actually works. So initialize C and A with 0. That is, initialize the accumulator and the carry bit with 0. And move the multiplicand into M and multiplier into Q. So at every step, you're going to check the bit in the multiplier. That is what we did in the previous case. So when we try to multiply manually, what we did, we have just taken a bit from the multiplier and checked whether it is 0 or 1. So we're going to have the multiplier put in Q. And this count is going to tell us how many number of times we need to do the multiplication operation. So it depends on the number of bits that the multiplier and the multiplicand has got. So if the multiplier has got n bits, then you're going to have n number of multiplications done. So if the multiplier has got only 3 bits and the multiplicand has got 4 bits, then to adjust the number of bits, we just make it as 4 actually, right? So n is going to be equal for both multiplicand and multiplier. So we are not going to compare the number of bits in the multiplier and multiplicand. Instead, we just make it common and have it as n and stored in count here. I hope this part is clear. Right, so this is actually initialization part. So here, once the initialization is done, you proceed with processing the bits in the multiplier. So that is, you start with the multiplication process actually, right, after initialization is done. So to start the multiplication process, what we actually do is we have to take bits from the multiplier and check whether it is 1 or 0. If it is 1, then you're going to just copy the multiplicand, or if it is 0, you're going to simply copy 0 and do shifting. So copying 0 and adding 0 with partial product is not going to get any useful results. We are going to have the same result which was there previously in accumulator. So that need not be done. So what we do here is we check for the value in Q0. So Q0 is what? You can just see this. See here, we have taken the same example what we have taken here in this box. We have 11 and 13. So this is 11. This is 11 and this is 13. Okay, so we are not going to change the multiplicand at any case. We are going to only work with these 3 registers, C, A and Q. So C and A are initialized with 0. You could check this. C and A are initialized with 0, and you have the multiplier in Q. So multiplier is moved in Q, and you have count value to be, so I'll just write the count here, count value to be 4. These are the initial values. Now, after doing this, you come and check the value in Q0. So if this is Q, then this is going to be Q0, Q1, Q2 and Q3. So totally 4 bits. So you're going to check for Q0, the value in Q0. Okay, Q0 has got what? It has got multiplier in it. So you just take the multiplier and check the value in the units position or in the LSB. So it is 1. So if it is 1, what are we supposed to do? If it is 1, you're going to add the multiplicand with that of the accumulator content, because finally the result is going to be there in the accumulator. So all operation actually needs one of the operands to be present in the accumulator. That is the basic protocol. So every time when you're doing any arithmetic operation which involves say 2 numbers, then one of the numbers should be present in the accumulator, right? And the other number could be in some other register, or it could be read from memory. And if it is a unary operation, then the operand should be present in the accumulator. That is the rule, right? So here you have the accumulator filled with zeros initially, and this addition is going to be done with the content of the accumulator. So what is to be added with the content of the accumulator? It is multiplicand, because the multiplier has got 1 in it. So we just add this 1011 with the accumulator. Okay, so then we get the result as 1011. That is 0 plus 11 is going to get you 11. So we have it here, and now simply copy these numbers. So, and what you do is, after doing addition, you shift. So here the first cycle actually needs both addition and shifting. At every step we are going to do the shifting. That is needed here. At every step we have to shift and only then add. So every step has to be shifted. After adding the value to the accumulator, we need to go for shifting. So you could see the table here, all the 4 positions has got shift operation done. So after adding this, we just shift the contents of the accumulator Q and C. So if this shift is a logical shift, which means that this C is going to be filled with, this is shift right. We are going to apply shift right, and maybe I can just write it here. It is shift right. So shifting right, you are going to fill the leftmost position with 0. So that is logical shifting. Okay, in arithmetic shift, what you do is you just have the content of the last bit copied after shifting in the last bit position. Okay, so here we are not going to copy, we are going to simply fill with zeros. So how you actually shift? You just take this bit here. This shifting has to be done after adding. Okay, so move this one to the next position. Here this one comes here, and this one goes here. The 0 takes its place, and the C comes here, and this empty position is filled with 0 again. Okay, so you just put a 0 here and move all other numbers, all other binary bits 1 position right. That is what is shift right. Okay, so once this is done, what you have to do is, one step is over, so you have to decrement the count. So you could see that here in the flow chart. If Q0 is 1, if it is 1, then what you do is take M, that is take the multiplicand and add with the accumulator content, right? So when there is an overflow, when there is a carry out of this addition, that will be put in C. Okay, so if you have already 1 in C, then that 1 is to be considered, and the value, the resultant value what you get there will be put in C, and the extra bit will be discarded. Okay, and now after doing this addition, come do what? Shift the contents of C, A and Q 1 position right. And also the next step is decrement the count value. And now check whether the count is 0. Is the count 0? No, we have some more bits to be considered in the multiplier. So if it is not 0, go back and repeat the same set of steps. So we just count is not equal to 0, so we just go back. Now if you go back again, you check the value in Q. So what is the value in Q now? Q0. What is the value in Q0? Guys, are you there? Am I audible?
Yes, ma'am.
Okay, what is there in Q0?
0.
0. So if it is 0, because we have shifted, you could see that it is very clear. We have already considered the last bit or the bit in units position from the multiplier. Now we are just proceeding with the next value. So that could be visible. See here in that is what we have done here also, right? So we have taken the first bit and multiplied all the bits in the multiplicand and taken the partial product. Now the next step is to move on to the next bit in the multiplier. That is what we are doing here. So when you shifted, this Q0 has assumed this new value 0, which means that we are now considering the second bit in the multiplier. So now considering the second bit, you have to check whether you need to add, do add operation or simply shift it. So how that is going to be determined? It is going to be determined with the value in Q0. So if it is 0, then multiplying the 0 with this multiplicand is not going to get you any result. It is simply 0. Adding 0 with accumulator will also have not have any effect. Okay, so in that case, if Q0 has got 0, you need not add, you can simply skip that addition part. Okay, so that is what is being done here. Since Q0 is 0, Q0 is not 1, it is 0. So we just come here. If Q0 is not 1, then you come here and do what? Simply shift it. No addition required. Is this clear? I hope you are able to follow this. See, by hearting this algorithm is simple, but you need to know how it actually works. Why this has to be done? Why this should not be done? All these reasons should be known. That is why I am just explaining this. Or otherwise I can simply trace this and leave. அது புரிஞ்சுக்கோங்க ஏன் இதை பண்றாங்க அப்படின்னு தெரியணும். Only then it will be easy. You need not by heart in that case. Okay, so now you have value 0 in Q0, and so you're going to just simply shift what? C, A and Q, right? So shifting this, what you get? The 0 will vanish. Yeah, just moving out. So this 0 will come here, this 0 will come here, and this 0 here, this 1 will come here, and this 0 here. You're shifting right. So this 1 will come here, this 1 here, and this 1 here. So 0 will just go off. It is out of the register, right? There is no 0. And now coming to what is next? After shifting, you have to decrement the count. Okay, so count has become 2. So count is not at 0, so you're going to go back and check the value in Q0. So what is there in Q0? It is 1. If Q0 is 1, you have to add the multiplicand with the accumulator. So the accumulator has got what? It is 0, 0, 1, 0. Now adding the content of this multiplicand. So it is 1, 0, 1, 1. So this is after shifting. Now when you add this, what you get? You get 1 here, 1 plus 1 is 0, and carry 1. So 0 plus 0 plus 1, you get 1, and 0 plus 1, you get 1. There is no change in carry bit. So after addition, you have this number. So addition is done. Addition is done. You did not disturb Q. You will never disturb Q. You will only disturb A. That is, do addition with the content of A. Right? So now, once the addition is done, you have to shift. So at every step, the shifting is important. So you just shift the contents right. So when you just shift the contents right, you get 0, 1, 1, 0 here, and this 1 will come here, and this 1 will vanish. All these ones will take the respective positions after shifting it right. Okay. Now, again, what has to be done? So this has to be, so this addition had been done and shifting had been done, decrementing count. So what is count? Now count is 1. It has not yet become 0. So what you have to do is, you have to go back and again check the value in Q0. So what is the value in Q0? It is 1. So if it is 1, what are we supposed to do? Take the multiplicand and add. What is the multiplicand value here? It is 1, 0, 1, 1. Just add it, what you are getting in here. It is 1. 1 plus 1 is 0. And you have carry 1 here. 1 plus 1 is 0 again. And you have carry 1. 1 plus 1 is 0. And you have carry 1. So this carry bit is now populated with bit value 1. Okay. And the accumulator has got 0, 0, 0, 1. And the Q register has got all 4 ones. So addition is done. What is the next step? You have to shift it right. So when you shift it right, you get 1 here, and all the bit values will get shifted 1 position right. And you lose this 1. This 1 is lost. Now, after doing shifting, decrement the count. Now the count has become 0. The count has become 0. So if the count becomes 0, you stop. So we stop here, and now the product is going to be available in A and Q. So the content of AQ is now finally 1, 0, 0, 0 followed by 4 ones. So you could check the result here. That is what we got. So this is 11 and 13, and when we applied this technique, we got the result to be 1 followed by 3 zeros followed by 4 ones, which is equivalent to 143. I hope this is clear. Is this clear?
Yes, ma'am.
Okay. Now this is the hardware, abstract hardware unit for doing this multiplication. You're going to have multiplicand that stored in one register, and accumulator is going to store initially the value 0 in it, and multiplier will have the multiplier value stored in it. And you have the shift and logic, control logic here, and this is an n-bit adder. So this adder requires content to be moved from accumulator and the multiplicand, right? So these are the different units, and this marks the carry bit. Okay, this is A, this is Q, and this is M, the multiplicand, right? So every time you need to just do addition and also do shifting. So you can just go through this, and this is not the exact diagram, this is an abstract hardware implementation of this multiplication. Okay, so let us not just dig into it. And this part of the slide actually helps you understand the signed multiplication. But anyway, you have only unsigned multiplication in your book, but we need to also know how the signed multiplication is done. So I'll just roughly go through it. So in the signed multiplication, the numbers are going to be the signed numbers. The numbers can either have negative symbol or positive symbol attached with that. So here I've taken an example of negative number multiplied with a positive number. So in the case of multiplication, the sign bit is going to be treated separately. The unsigned multiplication, the sign bit is going to be treated separately. If the sign bits both are same, then the value is going to be positive. The sign value is going to be positive. Sign of the product, I mean. So minus 7 into 3 is going to get us minus 21. Whereas 7 into 3 or minus 7 into minus 3 will get us positive 21. Isn't it? So if it is if it is 7 and minus 3, then again the result is going to be negative. Okay. So for the sign bits has to be treated separately. You have to find XOR, that is apply XOR and find whether they are similar or they are dissimilar. If they are similar, then you're going to have a positive value. If they are not the same, then you're going to have a negative sign of the in the product. Okay, now let's see how this multiplication could be done with the sign numbers. So just strip off the sign bits. So I've taken only these 3 bits. Okay, I've just stripped off the sign bit. So 7 and 3. So 7 and 3 is an unsigned number actually. Okay, the same set of steps could be followed. So I've taken 0 in accumulator in order to initialize it, and C is also initialized with value 0, and we have the multiplier 3 in Q, and the multiplicand 7 will be there in M. Okay, so here I again check the Q0 value. If Q0 is 1, then I add this 7, the multiplicand here. Okay, so since it is 1, I've just added this 1 here, that is 7 with this accumulator. The resultant value is 111. Okay, so after addition we need to shift right. So when you shift right, you're going to strip off this 1 and have this 1 here in the LSB. Okay, this 1 coming here and this 0 here and this 1 coming to this place. Okay, I've just shifted it. This is what has been done. Okay, now after shifting, you also keep decrementing the count. So here the count was initially 3 because you consider only 3 bits in the multiplier and multiplicand, so that will become 2 here. Okay, now after at the second step, what you do is you again check the value in Q. So value in Q is what? 1. So if it is 1, you have to do addition and shifting. So add what? Add the multiplicand. So multiplicand is 7, so I just add multiplicand after shifting. So it is 1 plus 1 0, and here again another 1, so 3 ones will be 1 1. So here I have 1 0 plus 1 will be 1 plus 1 will be 0, so we'll have a carry here. So this is what the result we get after adding the multiplicand. So once the addition is done, we need to go for shifting, right? So when you shift, you get this 0 here. Okay, so again apply the right shift, this carry bit will come here and just infuse 0 into this carry bit. Okay, now check whether now you have 1 in count has to be decremented. Count has become 1, so it is not, it becomes 0. So you have 1, you have to proceed with the next step. So since check the value here in Q0 in that case. Q0 is 0. So if it is 0, you need not do any addition. Simply shift. So when you shift, you have the bit values like this 0 coming here and this 0 added at the leftmost position. And after shifting, you decrement the value of C, and C has become now 0. Right? So it has got decremented to 0. Now you have to stop, and whatever is there in the registers A and Q is going to get us the result. So what result you have here? It is 0 1 0 1 0 1. So which is equivalent to, so you are not going to consider this carry bit. Don't consider the carry bit. Carry bit is not going to add to the product. So only the content of accumulator and the Q register will get you the product. So content of accumulator and Q register is 0 1 0 101, which means that 10101, this 0 has no value. Okay, so when you just try to find out the decimal equivalent of this, it works out to be 21. So I have just worked it out here. So 1, 2, 4, 8, 16. This 8 and 2 has to be taken off. As sum up all the remaining numbers, it is 16 plus 4 plus 1, which is 21. So with this, add the sign bit. So sign bit is, since the signs are dissimilar, you're going to have a negative sign. So minus 21 base 10. I hope this is clear. Purida? Okay.
Yes.
Okay, ma'am. Thank you. Now let's see how this process could be speeded, or how can you make this work faster, right? So we have another algorithm for same multiplication, which is called as Booth's algorithm. This is very, very important, right? So this Booth's algorithm, it actually speeds up the process which was done previously, right? So here, what you have to do is you have to consider 2 bits. So Booth's algorithm, the important part, the Booth's algorithm is the value of this Q0 and Q minus 1. Q minus 1 is the bit position, which is an extra bit added in order to check whether you need to do addition or subtraction or simply shift. Okay, so here let's check how it actually works. So have in mind that this Q0 and Q minus 1. So this is not Q1, it is Q minus 1. So check the bits Q0 and Q minus 1. This table you have to remember. If both these bits have value 0, 0 and 1, 1, then you simply shift right. Okay. If the bits are different, if it is 0, 1 or 1, 0, then for the case of 0, 1, you add the number, and for the case of 1, 0, you just subtract the multiplicand. Right? So, yeah, the thing's the same here. Accumulator, we are not going to have a carry bit here. Instead, you're going to have this Q minus 1 added along with the Q. So, you have the accumulator and a Q register, which actually stores the multiplier as in the case of the previous method. And you also introduce a new flip-flop, which is going to initially have 0, right? So, initially, it will have 0. And the multiplicand is again going to be stored in M register. So multiplicand will be there in M register. I think this is 3. Okay. So now what we do is, as in the previous case, you initialize the accumulator and the Q register and also this multiplicand. So that is what has been shown here. A is moved with 0 and Q minus 1 is also moved with 0. M is populated with multiplicand and Q is populated with the multiplier, and also count is moved with the number of bits in the multiplier or the multiplicand. So since both are going to be same, you can take any one of these count. So it is 4 bits here. Okay. Now, how actually it works is, as in the very first step, you just simply check the values in Q0 and Q1. So this table is very, very important. You have to remember this. Okay. So Q0 and Q1. So Q0 and Q1 has got what? The bit pattern is Q minus 1. So it is 1, 0. So if it is 1, 0, you subtract the multiplicand. Subtract the multiplicand. So what is the multiplicand here? What is the multiplicand here? Multiplicand என்னன்னு கேக்குறேன் நான். Guys, are you following me?
Yes, ma'am.
Okay, what is the multiplicand here? This is the example taken. This is the example taken. So what is the multiplier and multiplicand here? If the problem is minus 7 into plus 3.
Minus 7 is multiplicand.
Multiplicand? Yes. Minus 7 is multiplicand. So you have to subtract multiplicand, and 3 is multiplier. Okay. And here it demands a subtraction of the multiplicand from the accumulator content. So subtraction, normally how we do, we just try to find the 2's complement of the number and add it. Right. So if it is A minus B, then what you do is A plus minus b. Both actually gives the same result. Okay, so this minus b can be got from complementing this b. Find the 2's complement of b, you get the negative form of b. Okay, so find the 2's complement of the multiplicand and add it with the accumulator content. That is what has been done here. So you could see it as minus 7 is 1011. It is in 2's complement. Okay, we are not using signed. This Booth's algorithm is for numbers in 2's complement form. Okay, it is in 2's complement. That is minus 8, 4, 2, 1. So if you just sum it up, you get minus 7. Okay, so we get bit pattern 1001 for minus 7. So finding the complement of minus 7, that is negating a negative number will get you a positive number. Okay, so now you can check. It is 0 here and 111 will add up to 7. So minus 8, 4, 2, 1 is again 7. Okay, it is plus 7 whereas here it is minus 7. I hope you follow this. Okay, so what you do is for subtraction again, you just try to find the 2's complement of the multiplicand and then add. It eases the process here. Instead of having a separate unit for subtraction, so separate component for subtracting binary bits, we just use the same device, that is the adder here, to implement the subtraction also. Okay, that is what the idea is. So here we just try to find the 2's complement of this minus 7 and add it. So 2's complement of minus 7 is 0, 1, 1, 1, that has been added. I hope this is clear. Okay, now adding these numbers, you get 1, 1, 1 and 0. So after addition, as in the case of previous method, you're going to have shift right done. So after addition, do shifting. So we just shift this one to q minus 1 and this q1 will take the place of q0 and it goes accordingly. And you just do an arithmetic shift here. So in the previous case, it was a logical shift. So you copy the 0 back to the last position. Is this clear? That this is one important point that has to be noted. In the previous multiplication, which was slower, we just added a 0 bit in the last position in the LSB. Whereas here it is arithmetic shift, which means that we preserve the LSB value in the last position. So this 0 is copied again back to this position. It is not a new 0 that is infused, it is simply the 0 copied back here. Okay, I hope this is clear. Now after shifting, the count has to be decremented obviously. So here it was 4, now it will become 3. Count will become 3. You could see here in the flow chart. So do arithmetic shift. So this actually helps you understand what arithmetic shift is. Just a moment. These are things that has to be noted down. So you do arithmetic shift and decrement the count. So after subtracting. So we have just subtracted because the big pattern what we had was 1, 0. So we subtract and then do arithmetic shift right and also decrement the count value. So count will now become 3. So here it was previously 4 and count will become 3. Okay. So now after doing the shifting, compare the values. So what are the values here? After shifting, in q0 and q minus 1, it is 1, 1. So you just take 1, 1 and 1, 1 means you need not do any addition, instead just simply shift it right. Okay, so since it is 1, 1, just only do shift operation, you are not going to do any addition or subtraction. Okay, so you just shift it here, shift it right and preserve the value and decrement the count. So count will become 2. Okay, now again check the values in q0 and q minus 1. So q0 and q minus 1 has got what? 0 and 1. Since the values are different, you either need to subtract or add. So for 0, 1 you add. So 1, you can just remember the decimal values. For 1 it is addition, for 2 it is subtraction. Okay, it is 0, 1. So you add and do shift right. So what you need to add here? So add the multiplicand. So adding the multiplicand, don't call for complementing the number here. It is simply just take the multiplicand and add. So what is the multiplicand value here? It is 1001 in its own form, right? I am not complementing it because we are not subtracting, we are simply adding. When you add, take that number as such and do addition. So when you add, what you get? 1 plus 1, 0, and this carry 1 here, and carry 1 will be taken here because these two bits is 0, and 0 plus 0 is 0, 0 plus 1 is 1. Okay, so after addition, what are we supposed to do? We have to shift it right, do arithmetic shift. So this 1 goes off and you take 0 now in q minus 1, and this 0 will come to q naught, and we just accordingly shift all the bits, and the last bit is preserved. Okay, this is preserved, and again you compare the value, you just decrement the value, decrement the count. So when you decrement the count, it has not become 0, it is still 1, so it is non-negative or a non-zero value. So you just again apply the operation here, comparing the values in q naught and q minus 1. So q naught and q minus 1 has got what? 0. So if the bits are similar, just shift it. So we shift the 0 here and shift all the other bits to 1 position, right, and preserve this bit 1. Okay, so the number 1 here is preserved. Okay, now after that you decrement the value of count, value of count will now become 0, so you're going to stop. You're not going to do anything further here, and you simply stop. And now take the value in A and Q, which is going to get you the product. The value in A is 1110. Okay, the value in A is what? It is 1110. What is the value in Q? Value in Q is 1011. You are not going to consider this Q minus 1. So AQ is the product. Okay, AQ is the product. So it is 1110, 1011. So it is minus 21. So if this last bit is 1, then it means that it is a negative result. So you can just apply the values here, the place values, and check whether it is working out to be minus 21. That I have done here to verify. So it is minus 128, and I can just start from here. 1, 2, 4, 8, 16, 32, 64 and 128. In minus 128 you have 1. So I have just taken minus 128. And 64 there is 1, and 32 there is 1. So taking 64 and 32. And this is 0, so I have just left the 0. And here you have 8 plus 2 plus 1, which is 11. This 4 has been left. 4 has been left, so I have 11 here. So summing all these positive values, I get 107, 128 minus 128 plus 107 will get us minus 21. I hope this is right and are able to follow me.
Yes, ma'am.
Okay. So now, in what way we can claim that this Booth's algorithm is faster? Any idea, guesses? So we are doing the same thing. Instead of simply doing addition, we also do subtraction here in some cases, or when the bit values are 0 and 1 and 1 and 0. Only for similar cases we do shift right. Only shift right, no addition or subtraction being done. So how can we say that it is going to work faster?
Ma'am, if the it is 0, 0 means we know it subtractively we should shift right. So say 0 is 1 means it we know it to shift we know it to add or subtract.
That is what, like exactly, you're right. So when you have sequence of ones or strings of ones continuously occurring in the multiplier, then you avoid this addition or subtraction. But that is not the case with the previous method. So in the previous method, what we did was, when there is one, what will be the thing, like we add it. When you have sequence of ones, then you continuously do addition. When it is 0, we simply do only shifting. Right? So when it is 0, that is when this bit is 0. When this Q naught is 0, we only do shifting. But in case of ones, continuous ones, we keep adding. But here, if you just look into this method, even in the case of continuous ones, it is just enough to do shifting. So you reduce the number of additions or subtraction drastically when the multiplier has got strings of ones. Right? So if the multiplier has got only ones, all ones and that, then you need not go for addition at all, addition or subtraction at all. You simply keep shifting. You get the result right. Okay, so you consider the bits in the multiplier along with the previous bit what it had. Okay, so this makes this algorithm work faster. Okay, so if addition and subtraction is going to be costlier compared with shifting, then this is going to help us a lot. This actually increases the efficiency of the processor by only implementing shift and not calling for adding or subtracting the numbers. Is this clear? I think Booth's algorithm is clear. All that you need to, I just summarize it. You'll just populate the multiplier in Q register and have the accumulator initialized with 0, and also introduce another bit called as Q minus 1, which will initially have value 0. So you have to compare the values in Q0 and Q minus 1. If the values are similar, then you go for shifting it right, and here the shift right operation is an arithmetic shift right, not a logical shift right, which actually preserves the sign bit. Okay. For the different values in Q0 and Q1, either you need to add or subtract the multiplicand. So in case of 0, 1, the operation that is performed is going to be addition. In case of 1, 0, the operation what you perform is going to be subtraction. Right? So this in a nutshell, you just try to go through this problem again, so it will be more clear for you. And here, taking this flow chart, I just simply go through this. So flow chart says that initialize the registers first and also initialize the count value, and compare the values in Q0 and Q1. The bit pattern in Q0 and Q minus 1 is 0, 1, then just add and then shift right, apply arithmetic shift right, decrement the count. If it is 1, 0, then do subtraction and do arithmetic shift right and decrement the count. For the other two cases, if it is 1, 1 or 0, 0, then need not do any addition or subtraction, simply just shift it right and preserve the value LSB and decrement the count. So these steps has to be repeated till the count becomes 0. I think this is clear. Shall we move on to the next?
Yes,
Or you need some time to
Yes,
go
ma'am.
through? Yes. Next is division. I think I have to zoom it in. Now let's move on to division. So division, basically you do long division with binary numbers. That is what has been shown in this box. So we have two different numbers. One is called as divisor. The one which actually divides another number is called as divisor, and the one that is getting divided is called as dividend, right? So you have two inputs, divisor and dividend. As in the case of multiplication, where we had multiplier and multiplicand, you're having divisor and dividend. And the results are going to be in two different positions. One is going to have a quotient and a remainder, right? So you have two parts in the results, whereas in the previous case it was only one result, which is actually called as product, right? So which was stored in the accumulator and the Q register. Here you're going to have two parts in the result. One is quotient and the other one is remainder. So accumulator is going to have or store remainder after the complete process, and this Q register will get you the quotient. Okay, so the problem here is we may have a overflow in the case of division, right? So when you try to divide a number which is very large, and if the divisor is very small, the quotient may be larger. The quotient may be larger than the 4-bit position that is allocated to store the quotient value. So if the quotient is 5 bits or more than 4 bits, then you are not going to get the right quotient value. Okay, so and you'll not have the right remainder stored in the accumulator. So that case is called as overflow case, which cannot be handled. So you have to accordingly adjust the size of the quotient register and the accumulator register, right? So now let's see, let us not bother about the overflow, because that is not being focused high in our book. So we just try to understand how actually the division takes place, division algorithm works. So before getting into the algorithm, let us see how manually we divide two numbers when it is represented in binary form. So here as an example, so we have a dividend of 8 bits and divisor of 4 bits, and how actually we check is, we just check the take 1 bit at a time from the dividend and check whether that is divisible by the divisor. This is what normally we do even in the case of decimal division, right? So if you have say 368 divided by 13. What you do? You first take the first digit in the dividend and check whether this digit is greater than this 13. If it is greater than 13, then we proceed with dividing. But if it is not greater, what you do is you just make the quotient as 0 and take the next number or the next digit in the dividend. And now compare this value, that is compare the magnitude of these two bits or these two digits what has been taken here with that of the divisor. So now it is greater. If it is greater, what you do is you try to find out how many times it goes and accordingly you mark the quotient value. Right, so it is 2 here, so we have 36. And now what you do? Proceed with next digit. Next digit is brought down. You do subtraction here. Next digit is brought down and check whether this digit what you have brought down is greater than this 13. It is not greater. And if it is not greater, what you do is you'll just try to pull one more digit down. But there are no values here, so we stop. And this becomes the remainder and this becomes the quotient. Okay, the same thing is being followed here. So what you do is you take the first bit. First bit is 1 and the length of the bit is very less than the divisor, so obviously it is not going to divide. So you just mark 0. And what you do is you just left shift the dividend. That is, you move on to process the next bit here from the MSB. Okay, so you just leave this 1, meaning that you shift it left and take this number. So this 10 is compared with the value of 1001. It is still lesser. So you mark 0 and move on to the next bit. Next bit is 10. Taking this next bit, you get the value to be 100. Again, this is smaller. So you mark 0. Quotient is marked as 0. And taking this 1. Again, it is 1001. 1001 is what? It is 9. Whereas here it is 11. Okay, so this is 11 and this part it sums up to be 9. So the value is still smaller. So you just mark 0 in quotient and move on to the next number. So if you just take the next number, then the value will obviously be greater because it is 10010, right? Which is obviously greater than this 11. So in that case, if the value of this dividend that is considered is greater, then you just mark 1 and subtract this. Okay, that is how it is happening. You do subtraction and subtraction result will be 111 and you just pull this 0, next 0 down. And now again compare the values. So if the value is greater, you put 1 here and subtract. So you get 0011. So you get only up to this, right? 0011. The value here is not greater than the divisor. So in that case, you mark a 0 here in quotient and pull the next number. So when you just pull the next number, what you get? So here I have put 0. So here you just take 1 and now the value is greater than this divisor. So when the value is greater than divisor, you just subtract, mark 1 here in quotient and subtract, and now you have remainder. There are no more bits available in the dividend, so you stop. So this is the logic behind. So at every step, what you do is you just shift it left. You are shifting the dividend left. Okay, so dividend is shifted 1 position left, and you just mark 0 in quotient if the dividend is not divisible by divisor, or if it is lesser than the divisor, or it is marked as 1 if it is greater than the divisor. You just subtract the divisor from the dividend in that case, marking 1 here in the quotient. I hope this is clear. So you have the quotient to be 1101 and remainder to be 100. Is this clear? So all that you need to understand with this division is at every step you compare the value that you consider from the dividend with that of the divisor. If the considered value is greater, then you mark quotient as 1, do subtraction. Okay? If not, you simply shift left and do what? You just try to consider the next bit. So considering the next bit, again you check whether the value is greater or smaller. If it is smaller, again you're going to mark it as 0. If it is greater, you mark 1 in quotient and subtract. Is this clear? Is the logic clear? This is the very idea behind the division. So that is what is going to be converted into algorithm. If you're able to follow this, then it will be easier. Is this clear? Shall I move on to the next part?
Yes,
Okay. Yeah. So now coming to the algorithm, we initially make initializations So accumulator is initialized with value 0, and M is moved with divisor, and Q is moved with dividend. Right? So dividend is 7. I have taken an example of dividing 7 by 3. Right? So 7 by 3, when I try to divide 7 by 3, you have to get the quotient is 2 and remainder is 1. Right? So 7 divided by 3, you get this goes twice, and I have 6 here and 1. So this is quotient and this is remainder. Let's check whether we are getting this quotient and remainder here correctly applying this algorithm. So here dividend is 7, divisor is 3, dividend is moved into quotient register. Okay, and divisor is moved into M register. You could see it here. Divisor is moved into the M register and dividend in Q register. Now also you mark the count value, because the number of steps depend on the number of bits here that is considered in the, we always try to match the number of bits in both divisor and dividend. So if the dividend has got 8 bits, then the divisor should also have 8 bits. So this will be 8 in that case. Okay, so here they have not shown it, so you should have equal number of bits, because one register cannot be of size 4 and the other one having 8 bit size is not possible. Registers will be of same size, right? If you want to have larger size of registers, then you will combine. So normally if I want to work with 16-bit numbers, then I'll just combine two 8-bit registers to work with. Okay, wherein one part of the number will be in one register and the other part in the second register, right? So all the registers in the computing system will be of same size. If at all you want to have a larger number to be worked with, you have to combine it explicitly. That is programmer's headache. Okay, so we just mark it as equal. So that count is taken to be n here. So in our case, both the numbers are 4-bit numbers, so the count will be 4. Okay, and the dividend is 7. So that is there in Q. So we have 0, 1, 1, 1. So I'm just writing the binary equivalent of it. And M is going to have the divisor. Divisor is 3. So even though 2 bits are required to represent 3, I'll just have it as 4 bits, because you should have equal number of bits. Okay. So divisor is 0, 0, 1, 1. So now the very first step is shift left. Shift left what? A and Q. So what I do is I just shift the accumulator content and the quotient value 1 bit position left. Okay, so shift left A and Q. So even before you check for the values in the divisor and dividend, the very first step is blindly shifting. Okay, so I just shift the numbers 1 position left and make this Q naught empty, or keep it empty without infusing any value into it, because this value is going to be determined by the process that we make here in the next step. Okay, so initially this Q naught will be empty. So normally when we just do shifting, if it is a logical shift, we'll just fill it with 0. If it is an arithmetic shift, we just try to have the value that is there previously there, that was previously there. But here in this case, it is going to be simply left blank, right? So we are going to fill it anyway, but as of now it is going to be left blank. So I've just shifted the values here. So this 0 has gone out. So 0, 0, 0, this 0 has come here. Okay, so the shift has been done like this. We'll show you. I'm shifting every bit 1 position left. So here, and this 1 has come here, and this is maintained blank. Okay, so after shifting, what I do is I just add the divisor. Subtract the divisor. I just try to subtract the divisor. So how do you subtract the divisor? By doing addition. That is what we do, right? So we try to subtract and check whether the number is greater or smaller. When the number is greater, when you get a positive value after subtraction, that means that the divisor is larger. Is this clear? So if not, the divisor is smaller, in which case the quotient has to be marked as 0. Okay, that is what I'm doing here. So please kindly note this point. So what I'm doing here is I'm just trying to subtract the divisor. So when I subtract the divisor, so I actually do 2's complement, a subtraction here. So find what is divisor. Divisor is 0, 0, 0, 1, which is there in M. Okay. To subtract, what I do is I just do A plus minus B, do addition. Right. So I find minus M. So what is minus M? 2's complement of this M will be minus M. So find the 2's complement, you get 1, 1, 0, 1. Isn't it? So I take this number and add. So this is basically a subtraction process. Okay, subtraction using addition. Okay, so you just try to negate the number and add it, which will get you a subtraction done basically. Okay, so I add these two numbers, that is 1101, that is minus 3 is now added. Instead of just adding plus 3, subtracting plus 3, I just add minus 3, which will again yield the same result. So 1101 will be added with the zeros, 1, 0, 1 and 1. So what this result means? This result means that this is negative. The answer is negative, which means that the dividend, the bits considered now in the dividend is lesser than the divisor. We have subtracted the divisor, right, from the from the actual dividend. This whole thing comprises of dividend. So I've just subtracted the divisor from the dividend, but I get a negative result. So if the result is negative, then it means that the set of bits considered now from the dividend is lesser than the divisor, and I have to just mark 0 in the quotient. Okay, so if this is 1, I mark 0 here in the quotient. This question mark has been moved with or just overwritten with 0, or this empty space Q naught has been moved with 0. I hope you follow this. If A is less than M, if A is less than M, then what you do is move this 0 into Q naught and also restore the value in A. You are not going to do any modification here. You are just simply going to have the number as it is. The content of dividend should not change if the dividend is not processed by the divisor, right? So I restore. So restore the previous value of accumulator into it again. Okay, so I just take the 0, 0, 0, 0 into accumulator. This will vanish. That is, that subtraction has been taken off. Right? It has not been considered. Because subtracting that, I could say that, see, I have considered 3. I have considered 3. I just tried 3 minus 13. So how can I check whether this 3 is greater than this 13 or not? Just do subtract and check. So subtracting, I get a negative number. If this subtraction yields me a positive value, so if you just subtract 13 from 36, then it will yield a positive value, which means that this 13 could divide this 36 at least once, right? But here this 3 cannot be divided by 13. This is clear. That is what is being checked here. I take a part of, see, now the dividend is assumed to be 0, 0, 0, 0, 0, 1, 1, 1. I consider this part. I considered this part. No, it is not. Consider this part. So it is not divisible, right? So I have just restored it. I have just restored it. Taken this value again into it, into the accumulator. Okay, I hope this is clear. If A is less than M, what is A? It is 1101, that is minus value. If A is negative, that is what has been checked here. Subtract and check whether A is negative. If A is negative, then what you do is restore the value and move 0 into Q. So restoring, how they do here, they've subtracted M from A. To restore, they've simply added M back to A. So that actually restores the value in A. I hope this is clear. Purida? Guys?
Yes.
Yes, ma'am.
Okay, okay. Yeah, thank you. So restoring the value back here, I get 0 in A, and this Q naught has become 0. We have marked it as 0 because we did not divide it. When you are dividing it, you are going to have 1 in quotient. But you are not going to divide it because it is smaller, so I just mark it as 0. Okay. Now after restoration, what you do? You just decrement the count also. So decrementing count, you get 3. Okay. So after decrementing, check the count value. Count value is not equal to 0 now. It is greater than 0. So you go back and do what? Shift left. Okay. So you are shifting the values 1 position left. So this 0 goes off and this 0 comes here. And this 1 here. And this 1, 1 and 0. And you have to wait to fill this Q naught, right? So when this is going to get filled? After doing the subtraction here. So again subtract. So we shifted. Now we are going to subtract. Subtract what? M from A. So subtracting M is adding 1101 with A. So adding 1101 with A, you get 1101. Again, the number is lesser. That is the part of the dividend what you have considered is lesser than the divisor, and so division is not possible. You have to consider one more bit. Okay, so I mark this Q0 to be 0. Clear? And also restore. Restore into what? I just take the 0001 again into accumulator. Okay, decrement the count, go back, do shifting left. So when you shift left, you get this 0 here, this 0 here, this 1 coming here, and this 1 here, 1, 0, 0. And now this is a question mark here. You have to check whether this has to be filled with 1 or 0 by adding this divisor here. So, or subtracting the divisor. So subtracting the divisor with the current content of the accumulator. After shifting, the accumulator content is 0011. Right? So you subtract this m. So add this 1101. 1101 is 1 plus 1 0 here, and here it is 1. So 0 here, again carry 1, you have 0 here, again carry 1 here, and it is 0. This carry, what you get out of this MSB will be discarded. Okay, because there is no place to store it, so it will just vanish off. So you have 0000 and 1100. So is this value positive or now negative? It is positive, right? Because this last bit is 0, which means that they are equal at least, right? So it is 0 here. What you do is, it indicates that the part of the dividend that is now considered at this point is divisible by the divisor. So you just mark as 1. Mark as 1, and you don't do restoration. So it need not be restored because you need to subtract it. So if it is possible to subtract, if the number here dividend is greater than the divisor, then you have to subtract it and get the result. So we have subtracted and we got the result, and quotient has been marked as 1, so no restoration needed here. You are not supposed to restore it. Okay, so you have to take the remaining values. This part has become 0, so you have to take the remaining values. So now do what? After doing this, again shift and decrement the count. So count will become 1. So you go back, so shift the content of A and M, 1 position left, and again this Q0 is a question mark here. You have to fill it up, and now again subtract the divisor. So when you just subtract the divisor here, that is an actual addition to complement subtraction we do here. So 1 plus 1 is 0, carry 1 here, so I have 0 here. This is 0 plus 1, and this is 0 plus 1. So we have 1, 1, 0, and this is negative. This is negative. So what I do is, I just fill this Q0 as 0. Fill this Q0 as 0. And also, since this is negative, you just mark Q0 as 0 and restore. So restoration will get you 0001 back into A, because this is not possible. Which means that the part of the divisor what you have now considered, part of the dividend what you have now considered is lesser than the divisor. So no subtraction is possible. You cannot divide. So we are not going to subtract in that case. So you mark the quotient as 0 and take the previous result. So the previous result was 0001. So that is now restored. So you could now check the restoration is now being done by again adding this m with a. So you subtract 2 from 3, you get 1. So to get back this number, add this m. So you just take, to add this number, you get 3. So that is what is the logic we use here. So we just restore the values. So now decrement the value and see after restoration you decrement the value and count. So that will become 0. So if it is 0, you are going to stop. Okay. So on having value 0 in C, the process will get stopped, and now you can check the remainder and quotient. So I said that the remainder is going to be in accumulator and the quotient value is going to be there in Q register. So remainder is 0001, which is equivalent to 1 in base 10, and quotient is 0010, which is equivalent to 2 in decimal. Okay, the number what we have taken, the dividend is 7 and the divisor was 3. So 7 divided by 3 should get us 2 and remainder 1. Quotient 2 and remainder 1. So we have got it. I think this is clear. I'll just try to trace this flowchart also. So we have just initialized and count was initialized with 4, and the first step what we have to do even before checking the values in A and Q and M and count, it is just shifting left the contents of A and Q. Okay, and subtract the divisor from the content of the accumulator. So if it is negative is having value lesser than 0 in A. So it means that the value is negative because the resultant value is always going to be stored in accumulator. So you check the content of accumulator. If it is negative, then you come and mark quotient as 0, restore the value, restore the accumulator content, and then decrement the count. If it is positive, then it means that the divisor can now divide the part of the dividend that has been considered and mark the quotient as 1 and then decrement the count. So if the count is not equal to 0, go back and repeat the same set of steps.